How much work is done by 125 mole of an ideal gas on its surroundings as it expands from a volume of 1.5 meters cubed to 3 meters cubed at a constant temperature of 20 degrees Celsius? So, to help us out with this problem and maybe the next few examples involving thermodynamic processes, I've recopied the table of formulas for thermodynamic processes so that I can use these formulas to answer the questions. And so, really, the first step when reading a question is to decide which of these types of processes is being described. And the clue for this one is it says at a constant temperature of 20 degrees Celsius. So, that tells me that we're working in the isothermal regime here. So we're going to use one or the other of those two. Wait, they're the same formula. We're going to use that formula, right? I was going to say one or the other of those two formulas there, but there's only one formula really for isothermal because it's both the same for work and heat. We're asked for how much work, so okay, but that would also answer how much heat. So really what I have to do is plug appropriate numbers into nRT times the natural log of the ratio of the final volume to the initial volume. And in this case, maybe the way that would look is I could say 125 mole, and R is the ideal gas constant, which is 8.314 joules per either mole Kelvin or Kelvin mole, I guess, depending on who you ask. And then maybe times 20 degrees Celsius. We can cancel that against the Kelvin, right? And then natural log of 3 meter cubed over 1.5 meter cubed. That, of course, this really is just equal to the number, whoops, not the number 0, but the number 2. So I'm so used to putting a 0 when I draw that arrow that I put that by mistake. But really, I'm just saying, let's just take natural log of 2. And depending on how much you remember about natural logs, I would say the most important thing is to know where to find the button for that on whatever calculating device you're using. In other words, make sure you can find the button and then put 2 in that function when you put this into your calculator. So when I put all of this in, I get like 14,407, which maybe I could look at that as, let's see, this should be in joules, right? I mean, if the temperature units cancel, if the moles cancel, then I get joules left over. We are doing a work here, and it could have been a heat, so that joules makes sense. But I'm going to maybe rewrite that as 14.4 kilojoules just to make it more brief. And I think I'm still a little bit over rounded here anyways. Maybe I could have just said 14 kilojoules given the way the numbers are presented to me. So let's go ahead and check that answer. Oh my, I think I must have made a mistake. So I'm going to say, if you want to, pause this video for a second. And if you haven't already been screaming at your screen when I made the mistake, start looking for it now before I resume and tell you what mistake it was that I've actually made. All right. I don't know if you actually paused or not, but let's look at what the mistake was. This is not correct right here. Temperature in all of these formulas really must be in Kelvin. Although when I said that right now, there's maybe a bit of a pitfall, because you'll notice that for 2 of the processes, it's a change in temperature. And if I had a change in temperature of 20 degrees Celsius, I would just say that's 20 Kelvin. But this is more of an absolute 20 degrees Celsius. We're staying at that in a constant way. But 20 degrees Celsius is really 293.15 Kelvin. So this part right here, that's no good. That makes this no good as well. So what I should have done is 125 mole times 8.314 joules per mole. You know, a clue that, of course, was there that should have maybe prompted me to think about this a little bit more is when I wrote the units for this 8.314 with the Kelvin, as is customary for that. And then I saw the degrees Celsius here. I should have thought about that a little bit more, but it's very easy, I think, to do what I'm doing here in writing and at some point realize, okay, maybe I skip writing it and I just start putting numbers into my calculator. I personally do that. And that's how I make a lot of mistakes, including this one, because it's really easy to accidentally just read off, okay, 20, put that in the calculator and not give it a second thought. And yet when you write everything out with, oh, I forgot the Kelvin here for units. I was about to say when you write everything with units, which I didn't do very well there, that was the clue, right? That I should have thought about that one just a little bit more as I calculated what this work is. And when I put this expression without all the units in my calculator, so 125 times 8.314 times 293.15 times natural log, or ln of 2 is what I put in because I know this is 2, right? My calculator then says 211,171. 211,000, I said, right? 171 joules. And if I count correctly, right, 1, 2, 3, 4, 5, at 2 sig figs, that is in fact equal to 2.1 times 10 to the 5 joules.